This is Mr. Martin. This video is a continuation of section 11.1 for Precalc Honors. We're continuing to talk about limits. So let's take a look at this list of properties. So if L, M, and K are real numbers, and we know that the limit as x approaches c of f of x is equal to the real number L. So as x approaches c, the value of this function is approaching L. And as x approaches c, g of x equals m. So again, as the value of x gets closer to c, the value of our function is getting close to m. Then we have this list of properties. Okay, so the first one is a constant property. We have a sum rule where if I have the limit of a sum of two functions, I could separate it into the two separate values. So they're pretty self-explanatory, and honestly, we don't use these very much. Most of the time, when we use our techniques for finding limits, we're going to use direct substitution and a bunch of other techniques. But for this first example, we'll take a look at how we would use the sum property and the constant property to solve this. And then after this example, we'll just look at our other techniques for solving them. So if I'm going to use my properties here, I could divide this, or I could split this up into the limit as x approaches c of x cubed plus 4 times the limit as x approaches c of x squared, and then minus the limit as x approaches c of 3. So again, normally we don't do this, and you don't really need to know how to split this up. Once we have this split up into the different functions, this would be like our f of x, our g of x, this would be a constant. Then we can use our direct substitution. So this limit here as x approaches c would approach c cubed. This part here as x approached c, the value of that would approach 4c squared, and then this would approach 3, so then it would be minus 3. Okay, so again, we're not really going to split things up like this. We would just use direct substitution, where we would substitute in the value for c in our original function instead of splitting it up into 3 separate functions. All right, so if we apply just the direct substitution to this, again, as long as we don't end up with undefined pieces, so for example 0 in the denominator, direct substitution is going to be the way we're going to do most of these. So the limit as x approaches c would be c to the 4th plus c squared minus 1 over c squared plus 5, and this would be our answer. So let's take a look if the limit wasn't some generic value c. So let's say we had the limit as x approaches 2 of x to the 4th plus x squared minus 1 over x squared plus 5. So again, just doing direct substitution, making sure we don't get 0 in the denominator. We have 2 to the 4th plus 2 squared minus 1 over 2 squared plus 5. So that would be 2 to the 4th is 16 plus 4 minus 1 over 4 plus 5. So that would be 19 over 9. So the limit of this function as we approach 2 would equal 19 ninths. All right, feel free to pause the video anytime you want to work out these examples on your own, and you could restart it to look at the solutions. So again, just making sure that 3 doesn't give us any undefined parts of this or things that we're not allowed to do with algebra. So we're going to substitute in 3. So we have 3 squared times 2 minus 3. So that gives us 9 times negative 1, or negative 9 And going on to part B, just checking 2 in the denominator here. That's not going to give us 0, so that's okay. So we're going to have 2 squared plus 2 times 2 plus 4 over 2 plus 2. So that's going to be 4 plus 4 plus 4. That's 12 over 4, which would equal 3. So if we were to graph this function, not really sure what it would look like, but we're just going to graph a little piece of this where here's x is equal to 2. And here's y is equal to 3. So whatever this function looks like, let's just pretend that it goes like this, and it's going to go on to the left and to the right. As I approach 2, so as I approach 2 from this side, and as I approach 2 from this side, we're approaching a y value of 3. So that's kind of a visual. Again, I'm not really sure what this looks like, but I do know that it's approaching the value of 3 from either side of 2. So keep that in mind when we're talking about limits. Because again, even though a function may not be defined at some value, we can still approach a value as we get closer to it. All right, so some other limit techniques. Foiling, factoring, finding a least common denominator if we're going to add some fractions to help us solve it, canceling things out, simplifying. Some of these we'll use together in a problem. So let's take a look at some examples. So for this example, if I substitute in -2, I'm going to get 4 minus 2 in the denominator, so I'm going to get 0. So I can't use direct substitution, so what I'm going to do is I'm going to try factoring the numerator and denominator and see what I get. So this is going to be the limit as x approaches -2. Make sure you carry this limit to the next part here until you're ready to substitute in -2. And if I factor the numerator, it's going to be x plus 3 times x minus 2. And then if I factor the denominator, it's going to be x plus, let's double check my work here. This should be x minus 3, and x plus 2. And then this would be x plus 2 and x minus 1. So I can see that there's a common term in the numerator and denominator. These can cancel out. So that's the canceling out technique. And now that I've eliminated this term, which would be 0 if I plugged in -2, I can use direct substitution. So I'll substitute -2 in the numerator, so I have -2 minus 3. Substitute -2 in the denominator, I have -2 minus 1, which gives us -5 over -3, or 5/3. So even though this function cannot be evaluated at -2, as x gets close to -2, this function is getting close to 5/3. Make sure you're getting help if you don't understand that concept, the difference between the function evaluated at -2 and then the limit as we approach it. Alright, so go ahead and pause the video and give this one a try, and then when you restart the video, the solution will be up there for you. Alright, so here's two different solutions to this problem here. Now, we can go ahead and we can factor the numerator because this is a difference of two squares, and we would get x minus 3 and x plus 3. And then the x plus 3's would cancel each other out. Then we go ahead and substitute in 3, and we get 3 minus 3 is 0. So this technique is fine, even though we can just use direct substitution, since substituting in 3 doesn't give us 0 in the denominator. And if we do it that way, it looks like this. We have 3 squared minus 9 over 3 plus 3, which is 0 over 6, which is just 0. Alright, moving on to another example. Again, we cannot substitute in 0 in the denominator, because we'll get something that's undefined. So when we have trig functions involved here, sometimes we're going to use identities to help us solve this. So let's do a little simplifying here. So this is going to be the limit as x approaches 0. And then the tangent is the sine x over cosine x. And this is all going to be over x. I'm going to make that x over 1. So this becomes the limit as x approaches 0. And then this is going to be sine x over cosine x times 1 over x. Do a little rearranging. I have the limit as x approaches 0 of sine x over x times 1 over cosine x. Again, just rearranging these two. And if you recall from a previous video, the limit as x approaches 0 of sine x over x, so we have the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x. So this we discussed in another video is equal to 1. And then if I plug 0 in here, it's 1 over cosine of 0. And the cosine of 0 is 1, so that's going to be 1 times 1, or just 1.